Okay, welcome. This is lecture 22, and we have two more lectures left, including today's. So we still have one new chapter to cover. And therefore, for the final lecture on Wednesday, I would like to start really at 12:30, and then I will try my best to finish everything within 2 hours. But if necessary, I will drag on a little bit. Okay, so if again, as usual, we have the video, so you can watch them. And the reason that this time we have to reduce the amount of break and extend a little bit for a few lectures is because this year, for some reason, the term is very short. Usually we have 13 weeks, but this year we only have 12. And therefore, that's why I need to catch up like this. Okay, but I believe you will be able to follow my videos. Okay, so for today, the announcement, we have assignment 10 ready, and this is the last one. And the deadline is next Wednesday. Okay, and I will talk about final exam on Wednesday. So 2 days from now. Okay, I will tell you the coverage. I will tell you some arrangement, some standard arrangement. So the announcement will be made officially on Wednesday. And don't forget, we have exercise classes this week. And this week, we are going to talk about chemical potential. And then we are going to talk a little bit more about these quantum statistics, but mainly the Fermi-Dirac. Okay, so this is something nice that will go well with the lecture. Okay, what did we do last time? So just a reminder, last time we started talking about Fermi gas. So the best place to look for the physics of Fermi gas, in fact, is the electrons in a metal. So those electrons in a metal are considered as a perfect case for testing the Fermi-Dirac statistics. So this is a non-interacting case. Of course, there are interaction, but then at this level of the course, we treat these collections of particles as non-interacting. Once you have interaction, they will have other factors coming in. For example, the effective mass will be renormalized. It won't be just the effective mass of the free electron. Okay, so those will be will need to be treated in a much advanced level. Okay, but at the level of this course, we can already see a few things we can fix. So one of the puzzles, we have two puzzles for this part of the course. The first one we already solved, and that is why when you take a metal and measure the heat capacity, why is the heat capacity so small? So whenever I say this so small, I really compare with the insulator. Okay, if I take an insulator and look at the heat capacity at room temperature, let's say we go to room temperature, we have an insulator. And an insulator means all the electrons in that materials are not going to be moving. So they are there to help you to form chemical bonds. So you can still have your solid states. You have your atoms and you have your electrons, and those electrons are there to form the bonds. And they are not moving around like what you would expect for metal. Okay, so in that case, you have some heat capacity. And you measure the heat capacity and compare with the case of a metal. And by doing so, you realize at room temperature, okay, I need to emphasize this, at room temperature, somehow this heat capacity from the electrons are not there. Another way to say that is the contribution to the total heat capacity by electrons are so tiny. And the heat capacity you see at room temperature is almost mainly due to the atomic part, the phonon part, the vibration of the atoms. Okay, so this is the way to interpret this. Okay, I write it in a very compact form, but there's rather long explanation behind. Okay, so in the last video, I also compared that to Dulong-Petit. So the Dulong-Petit result is 3R, right? At high temperature limit, the Dulong-Petit heat capacity for 1 mole of material is 3 times the gas constant. And here we should expect 3 times the gas constant divided by 2, but this has never been seen. Okay, and then we treated this in a rather intuitive way. Intuitive way means we analyze graphically the density of states for electrons, and then we took into account of the Fermi function, Fermi-Dirac distribution, and then we are able to come up with this expression here: G times G of EF times KB squared times T without this pi squared divided by 3. So for that kind of intuitive, rather hand-waving way to get the result quickly, we will not be able to get the prefactor right. So to get this prefactor right, you have to honestly perform all the integration. Okay, but anyway, this is of the order 1. We already discussed that. And if I take this expression, the full expression, and rewrite it in a different form, you will see this result. Okay, so this gamma tilde is this. So this is gamma tilde, something, a prefactor which is of the order 1. And if I rewrite this properly, and this is in your assignment, okay, the hint is this: you need to come up with a good expression for the density of state at the Fermi level. Remember, we have this G of epsilon or E, right, which is proportional to square root of E. So you need to manipulate that function, that rather complicated function, and evaluate that at EF, and that will allows you to write it in this form. So you have something of the order 1, you have something which is what I call the C, the heat capacity due to Drude. Okay, so this is the Drude heat capacity, the classical heat capacity, and this is the correction factor. Okay, this correction factor basically tells you the Fermi temperature. You can write it in terms of Fermi temperature. If you take EF divided by KB, is TF, Fermi temperature, and the Fermi temperature is usually at least 2 orders of magnitude larger than the temperature of the system at room temperature. Okay, so at room temperature, this is of the order of 10 to the 2 Kelvin, and the Fermi temperature is of the order of 10 to the 4. So compared with this scale, depending on where you are, this is always a small number, and that explains why your heat capacity is small. Okay, so this is something we covered last time. And the second puzzle has the same flavor. The second puzzle, which is also a good piece of physics, is if you take a solid, a metal, with a lot of electrons, and your electrons are spin 1/2, right? So you have a lot of spins. So these spin 1/2 particles, we treated this before. We treated it twice. Once, we just mentioned it briefly, that when you have spin, you can expect Curie law. And we used that fact to discuss cooling, the adiabatic demagnetization. That part of physics requires a Curie law. We did it once. And the second time we encountered this was when we look at the partition function for 2-level system. And there, because of the spin 1/2, we have exactly 2 energy levels, and we extracted Curie law back then. So you should expect a lot of spin half particles in your metal. You have so many electrons, they are moving around, you should expect them to contribute to the Curie law. And the puzzle here is this paramagnetic contribution is so small. You have the Curie law diverges, right? You have this 1/T dependence. So you should expect when you cool down to low temperature, you should have a lot of contribution. But the problem is this Pauli, the so-called Pauli susceptibility, chi, P, we always use chi, but here we should give a symbol P, and this P stands for Pauli. Pauli exclusions, Pauli susceptibility is so weak. This is so small, so weak. Okay, and even worse, it appears to be temperature independent. Okay, so that is a puzzle that we have to resolve. Okay, so let's do that. Before I move there, I want to just show this slide. This is a picture. It's a little bit misaligned. This really shows the platform. This 3 millimeter. Okay, this is something we have at CUHK. The result is rather old. I did this work when I first joined CUHK. So when I first joined CUHK, I decided to set up the heat capacity measurement to measure superconductors. So here I will just show you a few key points here. So in our department, we can measure the heat capacity of a piece of material, a piece of solid state material very, very accurately. So this is the kind of setup we have. We have a suspended platform, and this suspended platform contains a lot of electronics below. Okay, so this suspension is to make sure the heat generated in this platform does not leak away. So, you know, you want to measure heat capacity. What do you need to do? First, you need to be able to calculate the amount of heat injected or taken away. And second, you need to be able to accurately determine the change of temperature. Okay, dQ dt. And that is the heat capacity. And another thing to say is this is heat capacity at constant pressure, because this setup will be in a machine that we can control the pressure more easily than controlling the volume. Okay, the volume of our system. Okay, so this suspended platform, at the top you will see a piece. This black piece here is our material, and here is a superconductor. And the interest, we're interested in many things. Heat capacity is powerful. We can measure many things. But of most relevant here is to show you that if I say, if I give you a piece of material, I don't know whether it's metal, whether this material is a metal or an insulator, you can use heat capacity to find out. Why? Because heat capacity, as I say, heat capacity, where should I write here? Heat capacity you measure contains many contributions. The one contribution is the electronic contribution. Okay, the other one is the phonon contribution. And then you can have other contribution depending on how many degrees of freedom you can have to store this energy. Okay, so these are the basic. If you have an insulator, this C electronic goes to 0. So according to our theory, back here, the heat capacity is proportional to temperature. Okay, so C electronic is proportional to T. Okay, so I'm going to call this gamma T, not to confuse with gamma tilde, but actually they have the same meaning. Okay, this is a coefficient that is proportional to the temperature. Okay, so this is a heat electronic contribution. And the next one is the phonon contribution. Phonon contribution, our goal today is to show you at low temperature, this is T cube. This is the Debye T cube law. Okay, so here, these are the low temperature contribution, low T. And what do I mean by low T? So low T means T has to be lower, much, much lower than the minimum of some energy scale. Okay, for this to be true, I need to be lower than the I need to be much lower than the Fermi temperature. Okay, then I will recover this linear term. And to recover this T cube term, I have to be much lower than the Debye temperature. So this is the symbol for Debye temperature. And you will see this treatment either today or on Wednesday. Okay, and how do you prove that? So the way you prove that is you do your measurement, you go to as low as possible. So we are talking about 40 Kelvin square. Okay, so if you take square root, you are at about 6 Kelvin, 7 Kelvin. Okay, so this is the kind of temperature you need to see this effect. Okay, you measure heat capacity from low temperature to as high as you want, and then you go to the low temperature part, less than 6 Kelvin, 7 Kelvin, and search for this kind of dependence. And that is the meaning of the bottom curve here. So because how do you tell you have electronic contribution? Here, this is plotted as C over T versus T squared. So C over T, if you take this form, you get gamma plus beta T squared. Okay, so if you have this physics, mathematically, you should have a straight line with a non-zero intercept. Okay, so this is non-zero intercept. This tells you gamma. Okay, so if gamma is 0, you have an insulator. So when gamma is 0, you don't have the electronic contribution, you have an insulator. And from the slope beta, you know you have this T cube law. So this slope tells you you indeed follow the Debye T cube law. So this is due to Debye T cube law. Okay. And here, this is low temperature limit, you have this, and when you increase the temperature, of course, you will pick up this. This is no longer the low temperature approximation. So eventually you go up and then saturate. Okay, but at low temperature from beta, you can then calculate the Debye temperature. Okay, so this is nice and consistent. We have indeed have a metal, and this metal contains electrons, mobile electrons, that we can pair up these electrons, and the electrons can undergo a superconducting transition. Okay, and as I said, this is a superconductor. And one more thing, maybe just for fun, what is this? Can someone guess? Now, this is an educated guess. You should be able to get quite close, but if you don't know this system, you might not be able to get to the precise nature. But just in the chat, let me know why do we have this feature. More? Okay, I get 2 good answers. 3 good answers. Very nice. One more. Okay, so this is a phase transition. This corresponds to a phase change here. Okay. So this is a way for us to detect that there is a phase transition. Okay, next, for those 5 students who answer, or actually for everyone, tell me, is it a first order or a second order phase transition? And why? Okay, time is limited. Otherwise, I would give you more time to play. This is a second order phase transition. Now, you might think this blow up. Actually, it doesn't blow up. Now, I cannot blame you. Maybe on this scale, it's hard to see. So if you go back to the chapter on phase transition in thermodynamics and just play with that, the second order phase transition part, you know, I have some figure to show. And you will see when you get this kind of rather asymmetric jump and then down like that, in heat capacity, C versus T, this corresponds to, this is a good sign of a second order phase transition. Okay, this has to be related to the entropy change. Okay, here your entropy doesn't jump, but the entropy shows a kink. Okay, and if you differentiate once more, that kink will show up as a jump. Okay, so it's a second order phase transition here. Okay, the detail, now thermodynamically, you know, this is a second order phase transition. And for my group, we study a lot about this guy, this feature here. We play a lot with this. We try to suppress this, control this, and try to see whether we can enhance the superconducting phase transition when we change this feature. So there are a lot more stories behind this. And I can tell you, this is a structural phase transition. So above here, this is, let's say, don't worry about the structure detail. This is structure 1. And below, when you cool down, you have structure 2. Okay, so it's a structural phase transition and it's a continuous phase transition. Okay, enough for now. Let's move on. And remember this, I don't want to show this slide again. I just, first, remember that I need to show you why we have this T-cube contribution. And you should appreciate this because when we talk about Einstein model, in the Einstein model, the heat capacity doesn't follow a power law. It actually follows exponential decrease. Okay, that is to say, if you cool down, your heat capacity goes down exponentially. Exponential is much faster at this temperature region compared with the power law. Okay, and here, this is one way to say that is Debye is correct and Einstein is wrong for this problem. It doesn't mean that Einstein, the harmonic oscillator treatment is completely wrong. There's some other usage. And that kind of usage is when you have something called the Einstein solid, when you have a very complicated crystal structure where the structure contains like boxes or cages, where you have some atom inside the cage, and this atom cannot talk to the equivalent atom outside the cage. Let's say if I move to the neighboring solid cell, unit cell, there's another structural equivalent. And the coupling is very weak. And in this case, we can actually have a situation where the physics of the contribution of this atom is a bit like what would be described by the Einstein solid. Okay, so here Debye is correct, and I need to tell you why we have this T-cube. And the third thing is to really show you some real data, and the data is measured in-house at CUHK. So what you are, again, the main feature is what you have learned so far is not completely just removed from you. It's actually quite close to reality. Okay, too much excitement. Let's move on to paramagnetism. Okay, the second puzzle. Why is paramagnetism in a metal so much weaker? Okay, so we can really do something very similar to the heat capacity. So let me first explain this figure. So this is a figure I gave you in the note as well. So you know this is the density of states versus energy. So I choose to plot it the different way. In the past, I always plot G of E versus E. And now I choose to put my energy axis vertically. And then I split this into two contributions. I'm going to, now this is for electron. Okay, now I want to consider the spin species. So for the spin up, I will give it 1 G up. And for the spin down, I give G down. And that is why this is actually increasing G. and this is also increasing G. So this is a positive direction. This is the positive direction. Density of states is always positive. Okay, so this figure, first you need to understand the way we plot this. Okay, so even if you go towards the left, it doesn't make it more negative, it's actually making it more positive. Okay, because this is always positive. Okay, so I'm going to split into two. In other words, you can say it like that. We know the form of this density of states. So I can write G up to be half of the total density of states. And of course, G down can be written like this too for here. Okay, so we need to discuss what happens when you apply the magnetic field. When you have, and we are going to stay in the zero temperature limit. Okay, so the spins of the electron can be either parallel or anti-parallel to the magnetic field. So I'm going to apply some field soon, and this is a series of events that you are asked to follow. And the magnetic moment due to the spin is Bohr magneton, right? So this is the moment. This is the moment, the magnetic moment, the magnetic moment. Okay, and what is the magnetic energy? So this is where you need to be careful. Okay, the magnetic energy will be different for different spin direction. So the magnetic energy this is Bohr magneton. So Bohr magneton times the field you apply, and that is the magnetic energy. But there's a sign here. This is everything. This is will determine the picture here. Okay, so this magnetic energy is negative when your spin is parallel to the field direction. Okay, and therefore, if it's anti-parallel, you will have plus. So this is higher energy when spin is anti-parallel to B. Okay, and therefore, the difference in the energy, in the magnetic energy, will be the difference between the two. And every year, very strangely, when I ask this question, people give me 0. I don't know why, but the difference is 2 mu B, 2 mu BB. Okay, so this is the energy difference. And the electrons will want to reorient themselves until they are more parallel moments than the anti-parallel ones to lower the overall energy of the system. Okay, you apply some field, you have this kind of difference in the energy, and for the system, the entire system to gain, to lower the energy, some electrons will want to reorient itself, right? So you like to lower, so how do you lower? You want to have more parallel than anti-parallel. Okay? All right, I want to stay at t equals 0, so I want to stay at t equals 0. Originally, this is the picture I would have without applying the field, right? Without applying the field, but I can somehow group my electrons according to the spin species. And now, when I apply the field, I will have this physics kicking in. So the one that's anti-parallel, all of them will gain this energy, right? So all of them will go up in energy. And you can imagine the entire population, right? What is the meaning of this area? Right? This area shaded in this kind of direction. What is this area? This area is actually the integral of the Fermi function times the density of states times dE. Okay, so you have seen this before. so the area, this area, I will draw it here. Whenever you want to count the number, how do you count the number? You count the number by taking the integration G, you integrate the density of states times the Fermi function. And then this is some appropriate limit. Here it will be from 0 to EF. Okay, 0 to EF. And this area tells you the number because at t equals 0, this is 1. This factor Fermi-Dirac is 1. So you basically integrate this G of E dE, which is the meaning of area. Okay? All right. So this entire population will move up in energy. And how much does it move? It will move up by mu BP. Okay, and those that are parallel will move down in energy. And how much do we move? We will move by the same amount, mu BP. Okay? All right, so we are ready to do the calculation. When you have a situation like this, now I won't write, okay, this is in the note, but I say it already. Maybe let me just mark this for you. So this difference is the change of the energy, right? So you move up, this one move up by mu BP. So this O2, the difference between O2 and O1 is precisely 2 mu BP. Okay, so the electrons will want to reorient itself to lower the overall energy. How do we do that? You see, these electrons here, they cannot go anywhere because it's locked. There's no states for it to go. Okay, and the simplest way is for the highest energy ones here to move down and fill this gap here. Okay, so there are some empty states here. Look. Right, so originally it's populated and now you move down and there are some states that becomes available. So at equilibrium, what we then have is you have this much electrons, right? As I say, the area is proportional to the electrons. So these will want to go and fill this gap here. Okay, and that will be a good happy state for the system. Okay, and to do this, really, you just calculate the area difference by integration. We can do that, but that again will requires more work. And just like our usual treatment, we are going to it's strange. We're going to do it without, I don't know why it's here. This is after moving. Okay, we are going to do it without worry about this tiny difference in the area. Okay, so we can do, this is the end result. This is the end result. Actually, sorry, just give me some time to fix this. Here, no. Sometimes this is very puzzling. Big paper is serving me well, but I'm still okay. Okay, wait, what did I say? Okay, I want to calculate the number of electrons that is affected this way. Okay, and the end result will be the one shown in the next page. So this is the end result. This is the equilibrium situation. So this is at equilibrium, Okay, so I want to calculate the susceptibility now. Okay, so the number of electrons that flip, the number of electrons, I will use this one. So the number of electron that flip the spin direction, that flip the spin directions. This is this area here. Okay, so we use this trick here. So we will have to calculate this delta n. This is the number that flip. It's some kind of integration. And we are going to take the Fermi-Dirac. And we are going to look at this much, right? So this is, what is this? This is G down. So we have G down of E, dE. Okay, with some appropriate limit. So if we have to do it like that, we have to integrate from EF to some appropriate limit. And the difficulty is to determine the limit. Okay, so I'm going to put a star. So this is the way to do it. The proper treatment will require you to do this. And the hand waving way is to just observe what happens here. I can just approximate this as a rectangle. So the approximation will be given like that. So this is approximating this as a rectangle. Okay, I write the result first. What is this rectangle? What is this area of the rectangle? This area of the rectangle will be this width times the height. So I will have mu BB times okay, let's call this the height, and the width is roughly the density of states at the Fermi energy. Okay, with a correction factor here. As I said, this kind of treatment cannot get this correction factor right. And this is G down. Okay. So this is approximate as a triangle, as a rectangle. What is a good symbol? P. Don't ask me why this is P. So I'm going to label this P. Okay. All right. So plug it in. This is just a half G mu BB. Okay, this is my delta n. Sorry, G E F mu BB. Okay, this is really cool. I'm nearly there. So if you have delta n electrons, this is the number of electrons. So those will come from here to here. So they flip from down to up. So the change of the moment will be 2 mu b per electron. So this much electrons will changes the moment. Will change from plus mu b to minus mu b. Okay, so the change of moment, magnetic moment, change. Again, this is 2 mu b per electron, not 0. Okay, and the total moment, this is 2 per electron, and you have delta n electrons. So the total moment change will be 2 mu b times delta n. Okay, now we can write the susceptibility. I put a P here to signal that this is due to Pauli. And the susceptibility is the total moment change due to the magnetic field applied, right? If you don't have magnetic field, you cannot induce this kind of change. So the susceptibility is actually telling you how easy it is to induce a change of moment when you apply some field. Okay, and we are talking about paramagnetism. We are still in the weak field limit. Okay, this weak field limit will come in soon. So this will be total moment change divided by the field. This is the applied field. Okay, we already saw this kind of treatment, identical treatment before for the Curie law. Okay, so how much change? We have 2 mu b, and then we go to the previous page and pick up this delta n. So the delta n here is a half g at the density of state at the Fermi level, at the Fermi energy times mu b. Okay, so I have a half g, the density of state, times mu b, and divide by h. Okay, and because we are in the weak field limit, we can relate this h field and b field. That is to say, the magnetization is very weak, right? So this is so for the discussion of paramagnet, the magnetization is weak, so we can write this result. Okay, then you can see already a lot of cancellation. You have these two cancel, you have mu b, Bohr-Mann square, and these are related by mu naught h, and the end result is this, chi p is mu naught mu b square times g of EF. Okay. At this point, hopefully you already can appreciate why this is the solution to the puzzle. The key is this. It's always this. It's always related to this guy. So this is the density of states. They're not evaluating for all. It's not the total density of states. This is the density of states at the Fermi level. So you have, if you add up all of them, you have a lot of particles, just like what we started with. But not all of them are useful. A lot of them are just like a vegetable sitting there doing nothing. The useful ones are the ones that are near the Fermi surface. Okay, so and in that case, what you really should count would be those that are at the Fermi surface. So you should count this density of states at the Fermi energy. And that is why the contribution is much lower than you would expect it if you take the whole population. The entire population are doing nothing. Only those tiny amount of them near the Fermi surface are contributing to this physics here. Okay, so this is my way to explain, but you might not like it. You might insist, okay, I want something a little bit similar to the heat capacity. I want a formula to relate the Curie law and the Pauli, the Curie susceptibility and the Pauli susceptibility. Okay, I can give you that, but you need to work a bit harder. So I would just say it can be shown. Who is going to show that? You are going to show that in the assignment. So it can be shown that from here, you will have some factor again, which we cannot deal with carefully. So there's some factor, but those are not important. This can be written as 3/2, so that is the factor, times T divided by TF times N mu naught mu B square divided by KBT. Okay, if you manipulate this using the same trick as the ones for heat capacity, that is to say you rewrite this in an appropriate way, you get this form. And this form is very transparent here. Why? Because now once you write it this way, you realize this is your Curie susceptibility, this term here. And this is a term of the order 1, And this is your correction term, which is tiny. Okay, so this is at any realistic temperature, you are much lower, you're much cooler than the Fermi temperature. And therefore, this correction term will slash down your chi Curie by a factor of at least 100 or 1000, depending on where you are. Okay, and that explains why the Pauli susceptibility is so small. Okay, now I think this is cool. You see, you can do full integral. Maybe at some point of your career, you are going to do it step by step, and you find that you get this result perhaps with a better numerical constant, depending on how you do the approximation. And depending on the dimensionality as well. This is another factor we should keep in mind. Okay. Now we are entering the final part of the course. We are going to discuss different statistics. And now we are going to look at 3 problems. Okay, so in the remaining 1.5 lectures, we're going to look at 3 problems. The first one is photons. So we are going to look at photons. Then we are going to look at phonons. Okay, this is just for completeness. I could have skipped this one, but I really want to tell you why you get this TQ law. And at the same time, you will realize these 2 problems are very similar. Okay, and of course, if we want to do this properly, really properly, we need to explain a few things. We need to solve Maxwell equation here. I'm not going to do that because I assume you have done it in other courses. We are going to start from the density of states. And if you want to do it properly, you need to start from solid state physics way of treating the crystal structure, and you go to reciprocal lattice. Then you solve the normal mode problem for a chain of atoms connected by springs. Then you get the dispersion relation. So basically, what I'm going to do is I'm going to borrow the dispersion relation, the energy momentum relation from your other courses, and then just plunge in and give you the result. Okay, so these are the second problem. And the third problem is the so-called Bose-Einstein condensation. So I'm going to treat this briefly. And then I will close the course and I will show you where to learn more if you are interested to learn more about BEC. This is a very, very interesting state of matter. You will have very coherent particle. All the particles can occupy the ground state, and you have this coherent wave function, which we call the macroscopic wave function, and it can be treated in a similar manner together with superfluidity. That is, you have the flow of fluid without any viscosity. So this is called the superfluidity. Another another coherent state you can realize is superconductivity, where you have charge. If you like, you can think of it as the superconductivity. Superconductivity. And in fact, I will also recommend you a book that if you are interested to learn more in summer, you can read all 3 together. There's one book that treats these 3 phenomena in the same book. Okay. Okay, so my plan is rather busy. So here, okay, what about we take a quick break, 6 minutes, And at 12:30, let's begin from here. Just follow this sequence here. Okay. So come back at 12:30. Okay, welcome back. So we should start from photons. So photons and then phonons is very similar. And for both photons and phonons, this is due to the lattice wave. Again, we need to realize that this is really some virtual particles. So these two, let's put some remark here. So these are some virtual particles. Okay, and here, this one, we are going to talk about particle with mass. Okay, so here will be, for example, we are going to talk about helium, but a particular type of helium. Helium, we have two isotopes. We have helium-3 and helium-4. It turns out that one is fermions and the other one is boson. So I will let you figure out which one is which. We still have time. We have 2 days to deal with this. And so if the spin is multiple of half integer, we will have fermion. Okay, so these are spin integer spin particles, so they are boson. Okay, so then for helium, this is really some real particle. We can talk about the mass of helium atoms, but we cannot really talk about the mass of photons. We cannot really talk about the mass of phonons. So these particles can be actually created or destroyed. So these are called virtual. That's the meaning of virtual. And for virtual particle, what do we need to do? So first, this can be destroyed or created. Okay, and how do I create more phonons? I will tell you how. I can change the temperature of my solid. I can raise the temperature and I will have more phonons occupying a particular state. Okay, and that is, you can think of it as, I will, for higher temperature, I will have the lattice wave with a larger amplitude. Okay, so that can be thought about like this. And how do I destroy photons? I can do that. I have a volume of volume V. I have a container of volume V. I can arrange for the photons to be absorbed by the wall. And in this case, I can destroy the particle. Okay, so for the virtual particle, the statistic is different. So for virtual particle, we do not have particle conservation. So we remember we have this term alpha times dn. When we derived the Bose-Einstein formula, right? This is the Lagrange multiplier alpha. And this term is there because of the fact that before we demanded the particle conservation, particle number conservation. And now you simply have to give up this conservation. Okay, so you have to set alpha to be 0. And remember, what is alpha? But this alpha is mu divided by kBt. And in this case, mu has to be 0 too. Okay, and the rest just follow. When I calculate the number, of particles in the K bundle occupying GK state, what are the possibility? And after we go through all this Lagrange method, we get this ratio. Okay, and this ratio will simply be e to the exponential of epsilon k minus mu divided by k bt minus 1. Okay, and we just have to set this to 0 and we are done. And in the continuum limit, so in the continuum limit, with 0 mu, and we will have Bose-Einstein distribution given by, so let me write this here, given by 1 divided by, I take this form, okay? So that's all you need to know. Then we can start. So let's start by giving you Planck's radiation law. Okay, I'll give you this law. It's So I will give you Planck's radiation law. And from there, you are asked to extract other laws that you can do in your assignment. Okay, so what we want to do, we want to consider a gas of photons in a cavity. So for simplicity, we are going to assume a black body cavity, which means you have a perfect absorption and perfect emission. And actually, this is called thermal radiation, right? This is the physics of radiation. And by the way, this cavity, just imagine this cavity to be this box we are talking about all along. This is a box with volume V, and I'm going to call it a cavity from now. And then I'm going to assume it's a black body cavity. Okay, and if you are at a finite temperature, you know, you can see this thermal radiation, but you might not feel that because at room temperature, this thermal radiation is in a different spectrum. It's not in the visible light spectrum for your eyes to detect. So you see a lot of at room temperature, you see a lot of infrared radiation. If you heat this piece of metal, let's say you go to the furnace and put it into high temperature, several hundred degrees Celsius, you will see it will glow, right? It will glow like a red hot, and you can feel that it's hot and very bright. This is the thermal radiation your eye can pick up because of the temperature. Okay, so something to keep in mind is we better be able to extract this temperature dependence. Okay, so when I give you the law, the first thing you should check is whether we have a nice temperature dependence. Okay, so what is the goal? Our goal, what do I want to get? I want to get something like this, so be careful. I'm going to explain soon. So we want to calculate this quantity. And this U is a little u. This is not the internal energy divided by volume. This is called the energy density in some books. I will use a different word. I will use energy content instead. Right? Because density, remember when we talk about density of states, you always have this density, this meaning of density coming in, which has nothing to do with volume. Okay, like GK, DK, this is the density of states, and in K space, right? Nothing to do with volume. The volume can, some book will define it with a volume, some book will define it without, but the meaning is the number of states per interval K. So this is the same. So that's why I always encourage you to write the argument and to carry the interval with you. Then you will not be confused. So anyway, this is the energy content. in the range of d omega, in the range of omega and omega plus d omega. Okay, so the range is d omega, but in the frequency, let me write it. The angular frequency range of d omega. Okay, so our goal is to get this for the black body radiation. And what is the plan? The plan is to find a way. The plan is to find a way to calculate first this n omega d omega, right? So h bar times omega gives you the energy. And then once we know this, we can calculate the energy like this. We just have to multiply by h bar omega, right? So this is the energy times the number, n omega d omega. Okay, so this whole thing must carry the meaning of energy, right? So just to remind you, how do we calculate this energy? We calculate energy in the discrete form by this sum, right? We have energy and then and dn, right? We have something like this before. So this dn in the discrete form, we have something like this, and in the continuous form, we will have something like that. Okay, so we need to know the density and then the energy carried by that photon with that particular omega. Okay, so and then multiplied by the number of them, and this is the way to calculate this. Okay, so in other words, you can identify this thing from here to here as little u of omega. So this is omega d omega. Okay, it might sound very difficult, but actually no, because we have done a lot of hard work before. If I start from scratch and ask you to do that, it will take a long time. But the reason we can do it quickly is because we have done this gk, dk. Okay, this is not the form we want because we have k, but you know you can change from k eventually to omega if you know the dispersion relation. Okay, I will take you through. I already said this last time. So remember last lecture I boxed one equation like this. So this is our starting point. So start from here. Two pi cube. Okay, so this is gk dk. You see you have the dk here. So sometimes people just write g of k as this. Okay, so this is the equation we box, and since this is a starting point, it's better if you know where we get it from. So this is equation 12.20. So now I think I still want to show it, and this is g of k d of k, because it's so important. You need to be convinced that this has been treated before. I can also ask you just to trust me. Okay, this turns out to be a design. Okay, yeah. Okay, and this slide is important because I taught you how to do this in 2D. I taught you how to count, and then I taught you if you use different boundary condition, you will always get the same answer. And I boxed this for you. The difference today is I changed this a cube to volume v. Okay, so this equation is the same as this one. Okay, G of K dk. Okay, and what is the next thing? The next thing is you write the dispersion relation. So the dispersion relation, which is the relation, the equation relating the energy to the momentum. Okay, so the dispersion relation for photon is very simple. Okay, how do you write the energy? The energy is, I will write a string of them because that will allow us to change the variable in the form we like. Okay, so we know the energy is h bar omega, if you like h bar. Okay, I personally like h bar, I don't like h. And at the same time, you know how to write the energy for photons, right? So this is a famous energy momentum relation, and where this c is the speed of light. Okay, and then the next thing you probably like to do is I don't like to use this momentum. I would like to write it in terms of k, right? If I have the wave, I know how to calculate, how to relate the momentum to the wave number. So I will have h bar times k times c. Okay, so from here, I can write omega is h bar sorry, ck, c times k. Okay, so this is what you need to remember, or you need to remember how to do it. And you will recognize that when I talk about phonon, I will not talk about this anymore. I will start from this relation, the corresponding, the phonon counterpart of this relation. Okay, so you need to pay attention now. This is for light, and we realize for phonon, we can write the omega for the phonon like this. The only modification is we do not use speed of light, but we use a much lower speed, and that is the speed of sound. And that will give you your T cube law just with this kind of ingredient. That sounds magic, right? You get these, and then you plug in something. You haven't done solid state physics. You just have to assume that you can accept the particle picture for the lattice wave, plug in the correct dispersion relation, change from gk dk to g omega d omega, right? That's the next thing I want to do. I want to change to omega space. I don't want dk space. I don't want the k space. Okay, so let's with this ingredient, the next thing, this is almost like a recipe book. I can then calculate g of omega d omega. Okay, I'm going to do it from here. This is more powerful, as I explained. This is more powerful. If you then put in the energy is h bar square k square divided by 2m, you will get the g omega or GEDE in that case to be the form derived long time ago. Okay, so that's why I boxed that equation, and I should box it once again. Important. Okay, so this starting point gives you a way to do this. So I can write, I would just treat the k and the dk. So I have v, I have this 4 pi omega square. So k square is omega square, and then I have this 2 pi cube. And don't forget the speed of light. So the speed of light is here. So I will have c. Sorry, is it correct? Omega square omega. Yes, in the end it's correct because I also have this dk to worry about. And this dk, once I change it properly, this will become d omega. Okay, so this 2 to the 3. Okay, all right. So this is it with one warning. This is the same thing we did before. We need to increase, now there's this factor here to discuss the degeneracy. And that goes in here, right? So for the electron, we put in a factor of 2 at this point, exactly at this point, when we change from GK dk to G omega, D omega, and that is due to spin. And here we have something similar. This is for photon, we need to discuss the polarization. Okay, and if I have a light wave propagating along some particular direction, I have 2 polarization. So I need to include a factor of 2. So this is this factor is 2 for light. Okay, and that's it. And you have a factor of 2 here. You have 4 here. So this is 8, and you have 2 to the third, which is also 8. And the end result is this V omega square, and let's cancel some pi. So I have pi square C cube D omega. Okay. Remember the goal. Our goal is to eventually reach here. So we have made the first step. We have successfully changed to omega. Okay, next. We can now calculate n omega, d omega. Okay, how do we do that? We need the occupation function, right? We need to consider that not all of the states will be equally populated. So this is governed by the statistics we are going to use. Okay, so here we can write G omega, D omega. We have the density of states. And now we need to go along the omega space and ask the question, which ones will be occupied? Okay, which one will be occupied depends on some factor, right? We will have this, depends on the energy of this particular state we are talking about, and the thermal energy your collection of photon is at equilibrium with. Okay, so the energy we are talking about will be h bar omega, and we compare that with kBt, right? Remember, there's no mu, mu is 0. And then we have this minus 1. Don't forget that. Okay. And next we will have this expression here. So we just copy omega square d omega pi square c cube times this whole thing. Okay, nearly there. So according to our recipe book, once we do this, once we know this expression, we know how to get this u of omega, because we simply have to multiply by h bar omega. Okay, so this u of omega, d omega, will be this h bar omega times this n omega, d omega. And you can see if I go through this step by step, it shouldn't be that difficult, right? So this is h bar omega, which is the energy of each photon with this energy. And then you ask how many of them are there. Okay, and how many of them are there depends on whether that particular energy level is occupied or not, right? If it's not occupied, we don't count. And that's why you need to calculate. You need to consider the occupation, this occupation factor. Okay, and this is Planck's radiation formula. So I will write the end result. Actually, I don't skip that many steps. All right, this is in my note too. So you get this omega cube. You get omega cube because you have omega square here and you have another omega here. And you have exponential h bar omega kbt minus 1 d omega. And this thing is the starting point for a lot of laws that you have probably seen somewhere else. So from here, you can derive those. So this is Planck's radiation formula. Okay, and how do you get the total energy? For example, if you want to get the total internal energy, so if you want to get total internal energy, and this is the big U, capital U. How do you do that? You integrate, right? You integrate from 0 to infinity. That's it. Okay, and if you do that, if you do what now you have this, right? You just integrate this formula like that. You get a famous result, which I hope you at least recognize the temperature dependence. Okay, so the end result is pi. Now there's a spatial integral that if you change a variable properly, you get some numbers. Okay, so it's basically some constant. Sorry, it's 3. Okay, this is what I want you to recognize. This is t to the 4th. Okay, so this is rather important for us, this t to the 4th, particularly for low temperature physicists. If you want to cool down to very low temperatures, we need to avoid this kind of very large heating source, right? Where I want to cool my experiment to very, very low temperature, we need to take into account of the fact that if I have a radiation source at 100 Kelvin, then I have to deal with 100 to the 4th. So if there's a way for me to reduce the temperature of my emitter, right? This is some kind of emission, right? Radiation. If I can reduce this to 10 Kelvin, then this radiation energy is very, very small. Okay, so this is the kind of thing we need to do. Okay, so the question is now here. Now Poon has a question about this whole space V. So as I say, you should not imagine this little u as now this u, this symbol. It's a bit unfortunate. This energy content or energy density is not big U divided by volume. Okay, so that's why I integrate in the energy space or in the frequency space. Okay, and the next thing I can do, let's take a new one, is I can also calculate the flux. So this is the energy flux. Maybe this is more intuitive for some of you. The energy flux through a hole of some unit area. Okay, and this is this symbol here, and that is 1/4 times the mean speed. I cannot do this energy density, so I will write it out. This is a internal energy U divided by volume. Okay, I don't want this little u to mean this this quantity for this part of the course. Okay, and then you get a quarter. For photon, you have C, and then multiply by the factor you can read from previous page. Okay, this comes from integration. So you do have to do some work to get these factors. Okay, and then you have this T to the 4th, temperature to the 4th. Okay, now this whole thing, this collection of constant, you can see now you will have some cancellation. This is called the Stefan-Boltzmann constant, sigma. Okay, so this is Stefan-Boltzmann constant. And this whole thing, this relationship is called the Stefan-Boltzmann law. Okay, and you can see again, it comes from Planck's radiation formula. Okay, finally, I want to define one thing for you. Define, so this is definition. This is called the radiance. Radiance. Okay, the symbol I will give is B sub omega. Okay, and this is defined as the flux, the energy flux of radiation per steradian in a unit omega range. Okay, now this steradian is the unit for a solid angle. Okay, it's just like if you have a circle, you can have an angle which is defined as radian. You don't like degree, you use radian. And steradian is the three-dimensional counterpart. So you have a solid angle that you want to discuss, and steradian is a unit of that. Okay, so the definition. So this is definition. Definition is 1 divided by 4 pi times C times this little u. Now you have to be careful. This is little u. I hope my writing is sufficiently clear here. Divided by big volume, big V. Okay, and then here you have h bar divided by 4 pi cube C squared omega cube, and this exponential h bar omega okay. Now why is this useful? Now suppose you have a way to measure this quantity, let's say of a very distant astronomical object. You have a way to measure this, and that will allow you to determine. Now this function is very, I plot it here for you. Okay, this one, B sub omega, and this function has a very characteristic form, which means if you are able to cover a wide range to show the peak, be careful, this is log versus log. So you need a very large frequency range. Suppose you can do it this way. This is your thermometer. You will be able to say, this particular object is at so and so temperature. Okay, and you can see the sensitivity to temperature. You take this data and you can fit it. to the formula. Okay, so this is one way. Another thing I should say is this is the cosmic microwave background. Okay, and as a function of frequency. So here is something similar to this form, but they are two different. So here we don't use omega, we use f in hertz. Okay, and we don't, this is not b sub omega. So this is defined in, actually, I will use the symbol for them. This is nu. Okay, this is b sub omega. And this is b sub nu. So it will be a little bit different. But if you do it this way, suppose you're given this data and you fit it, and they will tell you the average temperature of the universe. And you will find that this function can be fitted to a value of about 2.7 Kelvin. So this tells you the temperature of the background temperature of the universe, if you treat this as a black body radiation. Okay, so this temperature is about 2.7, and this is also something people always, low temperature physicists like, because they always say this is the part, temperature is the part which we can do better than nature. So you have 2.7 Kelvin, and in fact at CUHK, in my lab we go to millikelvin. And if you go to Professor Wang Dajun's lab, they go to even lower temperature to look at the Bose particles, right? So there they are looking at very dilute gas, and if they can cool down, they can condense those particles. Okay, so this is a part which we can do better than nature. Okay, so finally, I want to move to phonon soon. I know time is running out, but I can at least make some start. But before that, I want to make some comments here. Okay, and you can see from this slide that some people like omega, some people like nu, and you can indeed do this conversion the way you like. Okay, you can convert to nu if you know how to write the relationship between omega and nu, or f if you like. Right? There's a factor of 2 pi. This is not much of a problem. Why? Because you always go back to this kind of product. You know, it doesn't matter whether I look at omega or nu, this has to be the same. Okay, and then this allows you to change a variable, and you follow the steps I gave, you will be able to reach a different quantity here. Okay, and the constants in front most likely will be quite different. It's not something you can just read, right? You need to really go through all these steps and look at the prefactors carefully. This is not a problem, but the problem I need to warn you is this. If you want to convert between omega and lambda, you need to be careful, okay? Because this one is directly proportional. This one is inversely proportional. So when you look at the interval, it doesn't really matter. Now, inversely proportional means when you decrease omega, you have an increasing lambda. Okay, so you need to be careful here because you have this d omega, which takes the meaning of increasing omega, right? And you don't want to worry about the sign, otherwise you get the wrong result. Okay, so in this case, you should make sure you take into account of this potential time difference, sign difference carefully. Time difference. Okay, so if you take the absolute value, it will mean the interval. So what we care is the interval. We don't care whether we are going up in omega, or going up in lambda, going down in lambda. We don't care. We just want to make sure we get the interval correctly. Okay, so this is a comment, and this comment is useful because in the assignment you are asked to get to extract more laws. We already have the Stefan-Boltzmann law, but you can get 2 more. So one is the Rayleigh Jeans formula. Okay, and you start from my treatment, and here basically what you are asked is to look at U of lambda. So the Planck is very general, and historically there are less general laws or formula, and you can go from the most general one and try to deduce the rest. So this is U lambda d lambda at long wavelength limit, wavelength limit. If you have the long wavelength limit, you will have the short wavelength limit, and this is called the wind displacement law. Okay, so this is you are asked to look at this at the short wavelength limit. Okay, so have fun. This is we need to cooperate, otherwise I will end up spending too much time to extract this. I've done some groundwork for you. You are required to do a few more steps, then you can get the result you want. Okay, now this is next part is really something I like, and this is phonons. Phonon. So in solid state physics, we spend at least 3 lectures on phonons. Now, as I say, if you accept that we can have the dispersion relation for the quantized, for the lattice wave. Now we have the lattice wave. We solve this problem: mass, spring, mass, and then we have infinite number of them, and then we use the periodic boundary condition. Everything sounds very, very similar to the case of the infinite potential well. Okay, we eliminate the wall by taking into account of the periodic boundary condition. We can do the same thing here. Okay, and after this kind of treatment, you will have something called the dispersion relation. Okay, I don't want you to just leave my course and assume that this is completely hand waving. I want you to understand that if you take solid state physics, you get omega versus k, or we actually use a different symbol. We use q for phonon. Sometimes we use q, but it's just wave vector. It's the same thing. So this k is the wave vector. What kind of wave? The wave given by the lattice, right? So imagine these atoms can vibrate this way, right? And this one can vibrate this way. And this is not independent problem, because when this one moves, it's going to affect the neighbor. Right? These springs here are taking into account the nearest neighbor interaction. So this one will affect this atom because of the spring, and this one will affect the next one, and the next one will affect the next one. So you have a wave setting up like this, and this wave is given by this wave vector k. Okay, and if you solve it properly, you will get something like this. You have this is 0, and you will get dispersion relation that looks like this: linear at low k, and then it will begin to bend. Okay, so you will begin to show curvature. Okay, and you have other branch that are higher lying here, and those can be you can get them by solving this problem. Like for example, if you solve for this kind of problem, you indeed will get this kind of dispersion relation. You can even get this curvature. And if you let this atom to be atom A, atom B alternating, you will get another one which is at the top, and that is called the optical mode. And these are called the acoustic mode. Okay, so for today's lecture, I'm going to only assume that you have the acoustic branch. So I'm going to draw this as a straight line for you. And this is threefold degenerate. That is to say, I'm going to take these three and bunch them together as a branch with the average sound velocity. So this one will have different slope, right? The slope tells you the sound velocity. Okay, and the linear part is the part where the group velocity is the same as the phase velocity. And this is the part where you have propagation of sound wave. And in solid, it's very interesting. In solid, the sound wave can propagate in the transverse mode as well as the longitudinal mode. And that's why you have this kind of multiplicity here. You have three of them. So we are going to just group them together and use an average sound velocity, which is the slope of one branch. Okay, so I set this up for you. So here I would say originally three branches. One longitudinal, and then two transverse. Okay, and then approximate. We can approximate this. This is why I say this approximate as one branch. Actually, approximate as three branch with the same three branches with one single velocity. Okay, this is a straight line, so I can write omega is Vs times K. Just half an hour ago, I told you this is similar to the dispersion relation for photons. So you can think of this as the solid state equivalent of photons. So we call it photons. And everything really just carried over from the treatment of photons. Okay, so I can write, you see, this is very similar. I can write G omega d omega. And I would, my starting point is the same. I get this GK dk, I box for you. And I take that as my starting point. And this degeneracy factor is 3 because I have for each K point, I have 3 different branches. So for each dk, for each K point, I need to consider 3 different configuration. Okay, so this is 3 branches. So I'm going to do the star for you. So this is here. Okay, so this degeneracy factor has this origin. And the end result is 3b omega squared d omega 2 pi squared Vs. This is the speed of sounds cube. Okay, and the next thing is we need to have a cutoff here. We cannot just integrate from 0 to infinity. So we cannot just integrate this omega space to infinity. There are several ways to look at this. So first, let me write down for you. There will be a cutoff. Even though you draw a straight line, you cannot just go on forever. Okay, you need to cut off at somewhere, and this is what we call the omega d, the dBi frequency. Why do we need to have this cutoff? Because after all, this is the particle picture for the same problem. What is that problem? The problem is the problem of the lattice wave. So when we do this lattice wave problem, according to our knowledge from classical mechanics, we know this is the normal mode problems. And if you have n degrees of freedom, where n is the total number of particles, if you allow your atoms to displace along all three directions, you have 3n normal modes. That is to say, each point here corresponds to one normal mode. And therefore, once you count, if you count this properly, you have to recover the total number of normal modes. So let me write this for you. This 3n is the total number of normal modes. Okay, so this integral is finite, and you have this omega square here, and you are integrating some constant times omega square. If you do not put a cutoff for the upper limit, you cannot recover a finite number for the integral. Okay, so let me say this again. You are integrating this function omega square, which if you go to infinity, the integral will diverge, right? It will just keep growing. This omega square will keep growing, and then if you just keep adding, keep counting more area, it will just keep growing. But you have a finite number that you have to demand, and therefore you must have a cutoff. Now, if you are observant, you will see this is very similar in spirit. When we discuss the Fermi energy, we also have a cutoff, right? We have the density of states. We integrate from 0 to EF. And what is the cutoff? The cutoff is we must have a finite number of electrons in the system. And that is why you have EF there. You don't count to infinity. Okay, so this is why we have a cutoff, and this explains why. And you can also view this as a definition of omega d. Okay, if I ask you what is omega d, you can say omega d is whatever the upper limit defined by this integral. So this is used as a definition for omega d. Okay, if you plug in, you have your g of omega, d omega. If you plug in this expression and integrate, you can get your omega d. So I will write you the omega d first, and I will let you go in the next few minutes. Okay, so this is a natural point to write it. So if you do this integral, you get b 2 pi square vs cube omega d cube is 3n. Okay, so you know the number of particles in your system in principle, and the rest are just constant. And this allows you to define omega d. Okay, and finally, I want to just say this. Then I will let you go. The other way to understand why we must have a cutoff is like this. If you have a maximum, the cutoff means there exists a maximum omega, right? So what is omega? This is some kind of a frequency, and therefore, if you have a maximum, there exists a maximum omega. So this means they must have a minimum lambda. Okay, so that is to say, in your solid state system, there is a meaningful minimum wavelength. Below this meaningful wavelength, the whole thing is meaningless. Okay, and why is it the case? You can imagine this. If I set up a lattice wave, suppose I have my atoms here. If the wave come in, these atoms will go up, this atom will go up a little bit, this one begin to go down, this one go down more, then I set up a wave. If I have a wavelength which is very small, suppose I can create any wavelength I like. I have a wavelength like this. I can do something like this. But why is it meaningless? The reason this is meaningless is this kind of lattice wave will have no atom to fill it. I can create mathematically any wave I like. But once I go to my solid state system, there is no atom here to fill this kind of wave. So what is the point of using such a wavelength? I would just take a much lower frequency, much longer wavelength, such that these 4 atoms will feel the corresponding change. Okay, so this is why there's a minimum lambda, and this minimum lambda is comparable to the lattice spacing A. Okay, and that is why we do not need a wavelength which is much lower than A, and that is why there is a cutoff omega d. Okay, that's all. Now, one more thing. Now, this kind of thing is related in the signal processing theory. This is what we call the Nyquist theorem. If you want to sample a frequency correctly, you must not undersampling. Now we are talking about frequency. You must not undersampling, otherwise you get a frequency which is wrong. And this is called the Nyquist theorem, the sampling theorem, but they are all the same. Okay, so I will let you go now. And sorry about this, and next lecture is likely to be a bit longer. And I will give you the heat capacity on Wednesday. Thank you very much.